Okay, I want to show you something very cool, very important. Let me kind of put this in a little context here. I want to make sure, I want to have as much time as I can to get this explained to you. Remember, let's everybody put all kinds of any distraction away. This I need undivided attention for this. This is big time. Remember when we were talking about taking derivatives, going way back when, which seems a long time ago now, and we looked at and we practiced using all the derivative rules. You know, we know a bunch of them now: tangent, cotangent, power rule, quotient rule, etc., etc. And then we were pretty limited though, because those only applied to situations. I'll give you an example. They only applied to situations like, for example, if I had, let's say, a derivative with respect to x of x cubed, we knew what to do, right? We don't even ask the one that's old here. 3x squared, but we were a little bit limited when it came to things like taking derivatives of stuff like this. What if I had x squared plus sine x cubed? Right? We didn't have a rule for that. But then we developed the chain rule, and all of a sudden we could handle all these other problems that were previously inaccessible to us. That was a good day in calculus. Well, we got another day like that today. I'm going to show you essentially the equivalent, and this is even more important maybe. I'm going to show you the equivalent maybe of the chain rule for differentiation. Okay, what this allows us to do, stuff like this. What if we want to calculate the antiderivative or the indefinite integral of, now we're fine doing stuff like this. If I just say x squared dx, you will all tell me what? Yeah. And plus c. Okay, good. But what if we have something like this, let's say? Now, we can do that one at this point. How do we do that one?
That's the root 3 plus x and that times x squared.
Okay. No, I can't do that.
Plus x.
Can't do that. Because we can't now, I understand where that's coming from, but we can't just reverse the, well, I don't want to say this. We can't differentiate product by, or factor by factor. We can differentiate or anti-differentiate term by term. But if there's a product of stuff here, it gets more complicated. Remember that we had,
Then you would multiply it in.
okay, good. What we would have to do is distribute the 2x through, right? And then just anti-differentiate term by term. Agreed? If there's a product there, it gets more complicated, because remember that when we differentiated a product, we had to use the product rule, and you can imagine anti-differentiation, which gets more complicated than differentiation. It's even worse. So products, there is no product rule for anti-differentiation. There's something somewhat similar to that we may get to. I don't know. It's possible, and that's kind of a higher technique of integration. Something for sure you'll do next year, but I don't know if we'll get to it this year. But that one we're kind of stuck with unless we distribute. And what if we had something like that? Then it even gets more complicated, right? Or what if that were a 2? What if that were 5? What if it were a 5? Heaven forbid, what if it were a 5? Then that gets really complicated, right? Then I've got to distribute that whole thing through, I've got to expand the binomial, then distribute the 2x through, and then anti-differentiate or integrate term by term, right? That gets to be kind of cumbersome. And then certain other antiderivatives we couldn't even do. Like what if we wanted to do, let's say, square root of x squared plus 1 times, to be convenient, we'll say 2x dx. We can't even do that one, right? That does not fit any of our standard forms. We have one that looks remotely similar to that, but it's not, that looks like the power rule, but we can only deal with the power rule if that were just an x in there, right? Then we could write it as x to the 1/2, but we don't know what to do with something like this. At this point, we just have to do that. We don't know what to do. Okay, yeah. But we don't want to just do that. We want to do something else. So I've got a new concept for you here. We can do what's called a variable substitution. Okay? This is a big deal in math. In math, and we do this in many different circumstances in math. A lot of times it's convenient for us to say, just out of the blue sometimes, we're just going to say, let's go ahead and let this variable equal this, in terms of, we're going to let one variable be related to another variable, just to make things look simpler. And that's okay to do. It's okay to do, as long as we establish what the relationship is, and we state it very clearly. We can always undo that move if we want to. So in this case, how about if we do something like this? How about if we say something like, let's go back to this one for a second. What if we made the substitution, let's let u equal, and that's the variable we choose for substitution, and kind of our short name for what I'm about to show you. Technically, it's called integration by substitution, but people just call it u-substitution, because we're going to choose a u that makes sense. What if we choose u equals x squared plus 1? Okay. Now, if we do that, what if I were to differentiate u? What do I get? Okay, good. So if I calculated du dx, I would get, differentiate, sorry.
Okay. So 2x.
2x. And if I were to write that derivative in differential form, now remember what that is, going back to last chapter. Differential form, remember, is where we're not differentiating with respect to something. We're just going to have the derivative of this equals the derivative of that, right? And that's what what do we do here to accomplish that algebraically? Yeah, I just multiply both sides by dx, right? And so I end up then with, if I do that, I just end up with du equals 2x dx, right? And really, you guys are good enough now that you could skip that middle step and just go from there down to there, right? You could just differentiate something in differential form, and that's fine to do. We just know that the derivative of u is du. The derivative of x squared plus 1 is just 2x dx, right? Okay. Now, if we try to relate that to what we've got up here, what do we end up with? Right. In fact, let's go ahead and I'll just get rid of this guy. We'll write him back up here later too. If I go back up here and I make my substitution, what do I end up with in terms of u's? Okay, well that's u right there, isn't it? I end up with u to the 5th times, what's all that? That's du. Wow, that was slick, wasn't it? Look what we accomplished there. Does everybody appreciate what we just did? We made something that looked pretty ugly, right, into something that looks really simple.
If you have to evaluate though, isn't it just going to be the same as the original?
Okay, you mean when I have to switch back, you mean?
When you have to evaluate, so yeah, right.
By evaluate, you mean when I have to revert back? We'll see.
Like
Let's experiment and see.
Like if you had a value of x and you have to go back in and solve it.
Yeah, well, we'll do that. We're going to write our answer in terms of x. And you're right, the answer might look ugly. It's possible. Possible that it will. We'll see. We'll see. What's the answer to that one? You know that one. That's just a straight power rule, right? That fits our standard forms. What's the antiderivative, or we'll start calling it the integral. What's the integral of u to the 5th du? Okay, u to the 6 over 6 plus some constant, right? So we get for our answer, there it is, that's our answer. But our original problem was written in terms of x's, right? We want to write this, we want to reverse the substitution, we would say, and go back now to x's. But we have that established right there. there's u, and there's du, right? Now, we don't need the du anymore, but we need the u, don't we? If I flip back, I just end up with 1/6 times u to the 6th is what? Okay, the quantity x squared plus 1 to the 6th plus c. How about that? That's not so bad, right? Now, if we had done this the old-fashioned way, it would have looked pretty ugly, because probably, well, not probably, what we would have gotten, had we expanded this whole thing out and integrated term by term, we would have gotten this long chain of answers. Well, if we were to expand this binomial, we'd have a long chain of terms, right? We would have had the expanded version of this, which would have been ugly to begin with, but it would have been very hard to recognize what it looked like in factored form. And remember that in math, what we're typically wanting, we want to express things in a simplified way, and we want things to be in factored form. We spend a great deal of energy and effort trying to factor stuff, right? Well, this is done for us now. So this is just an embarrassment of riches here. I mean, not only were we able to do this thing simply, we get an answer that's in exactly the form we'd like. Okay? What about that? What's that?
Why do you have to teach?
Well, we never, now this is one where, we never actually did much of the long way on this one. Very, very seldom did you guys actually, I probably never made you do that problem. Nope. No, and for good reason, because this is a situation where nothing is accomplished by the long way. The long way, now I'll argue, in my own defense here, that the long way, like with the limit stuff, is important to do. It really is. And you'll appreciate that as you go further in calculus, that you need to know that. But here, the long way does you no good. The long way is just the bad way. This is the good way. Now that we have this shortcut, this u-substitution, right? This is definitely the way we want to do it. Let's try one more of these, and then I'll show you the official formula. Let's go back to that other one I gave you. How about? What if, I think we had, what did I say, antiderivative or integral, I'll start calling it integral, of x squared plus 1 times, oh, I'll make this a little trickier, times x dx. Okay? Now that one is, you can't do it without making a variable substitution, a u-substitution. What would our u be here? And by the way, I want you to kind of don't feel panicked if the u's aren't always immediately obvious to you at first. This is where calculus really starts to become almost more of an art than just a straight math skill. Calculus, it really, and I know you've probably said this so much to you guys that you're getting tired of hearing it, but calculus is all about practicing. The more you do it, the better you get. And it's like playing an instrument. Math gets to be that way. Eventually you get to be intuitive about it. Picking u's for substitutions like this, and with the later other advanced techniques and integration that we'll maybe get to a little bit this year, but a lot next year for you guys. It becomes, you just start to see it easier and easier. The u typically, when you're making a variable substitution, typically, and I think the book talks about this a little bit, you'll want to read this section, or at least read through the important information. Typically, what you want to do is pick the arguments of functions. So when you have nested functions or compositions of functions, like this is two layers, right? I've got a square root of a polynomial. Well, whatever's sitting inside that square root is going to be a great natural choice for a u, because our goal is to get something easy to the 1/2 power, right? Now, probably you all would naturally do that anyway, but sometimes people do things like initially when they're first practicing this stuff, they take maybe just the x squared as being the u. But why not take the x squared plus 1? And with a little practice, those kinds of decisions and choices get to be more and more natural. But in this case, clearly the u that we want is the same one we picked last time, x squared plus 1. So du just becomes 2x dx. But now look what happened here this time. This time our substitution didn't work out quite as slick as it did before, right? When we go to make this substitution, let me do this. Kind of color code this. Oops, backwards. Let's make these blue so we can transition from red to blue. when I make my substitution to go from blue x's to red u's, well, this part works out great, doesn't it? Right? I just get the square root of u, which written as a power is what? U to the 1/2. But what about this guy right here? Okay, I could multiply by 2 over 2, but there's maybe an easier way to do this algebraically. What you want to do is when you want to finish your substitution, look for the part, this is accounted for, right? This is the part that's unaccounted for. Well, let's just go back to our substitution equations and let's find out where that sits. Well, there it is, right? That's the part that goes there, right? So to solve for that piece, I would just divide both sides by 2, right? That makes sense? And so we just get something like x dx equals du over 2, right? And so when I make that substitution, now how do I break that apart? Well, I could put the du right there. Where would the 1/2 naturally go most easily? Out front. Why not?
But then will you multiply through once you?
Oh, yeah, right. I mean, now 1/2, well, I mean, it depends. It depends. My goal here is to write the easiest answer, right? And a lot of times we'd rather have this factored anyway. And so really the 1/2 is already out there. We always have the option of distributing it if we want to. But that kind of depends on maybe the situation or how we're feeling that day. I don't know. So what's our answer? We get the 1/2 out front, but then, say it again.
It's 2u to the 3/3 over 3.
2u to the, hold on. How'd you get that? What is it? Forget the 1/2 for a second. What's the integral of u to the 1/2?
2/3.
Okay, that's probably what you said. I think it is. I know what you did. Yeah. Okay. So we got u to the 3/2 instead of dividing by 3/2 times 2/3. I know what you did. You were canceling stuff and doing tricky stuff. That's good. U to the 3/2 plus c. We can do that, right? Now, if we reverse our substitution, that just gives us 1/3 u, which is x squared plus 1, to the 3/2 plus c. Make sense? Okay. All right, well, here's what you see in the book. Someone who did this originally had a sense of humor, I think. There's 2 ways you can look at this. You can look at this as, but the top way is a little bit visually confusing to me. If you have the integral of f of g of x, so you got a composition of functions, and what you see there is that you have f of g of x times g prime of x dx, right? Then that works out to be the antiderivative, capital F, of g of x plus c. That's confusing. What's easier to do is think of this in terms of a u substitution. If we can write this as, be careful here, f of u du, then the answer is capital F of u, the antiderivative of u plus c. Okay? And this way probably makes a lot more sense now based on what we just did. If we can pick this u substitution so that all of the x's go away, and I write this in terms of u's, then I can simplify things greatly. Okay, let's look at maybe a couple more examples, and I want to look at one that doesn't, at what's called an incomplete substitution, and how we deal with that. What would you do with? Let's do this one. Stare at that for a second. Now, we could do this if we really wanted to rely on a whole bunch of trig identities. We could do this without a u substitution. we could write the sine of 5x as something like the sine of 3x plus the sine of 2x. And then we could take each of those, and and just keep writing those in terms until eventually we got down to just x's. But we'd have this big chain of trig stuff going on. It'd be a real pain. Okay? Is there a much shorter, more efficient way of doing this? Does anyone want to try a u-substitution on precise here? Because you can't do that. 5 is stuck in there, isn't it? Right? I mean, unless we want to make a whole bunch of switches, angle switches. Anyone want to try on a u here?
What do you mean?
Now, don't bite off too much here. You want to pick something. What would, and you kind of ask yourself here, if only I had what? I mean, sine's not so bad by itself. What's the problem with this guy? The 5, right? So what's the smallest u substitution I could pick here that would do the job? 5x, how about, right? If that were just the sine of one thing, we'd be fine, right? So if u equals 5x, du equals what? Well, now what's if 5 dx, right? Now, does everybody see that? First of all, sometimes those simple ones like that seem the weirdest. Does that make sense? Okay. Then if I make my substitution here, what have I actually got? Sine of u. And what is the dx then? Oh, okay, that's a 1/5 du, isn't it? Right? 1/5 du. And so our answer is, what's, again, 1/5 stuck out front. What's the integral of sine u? Okay, negative, I can stick that out front. Cosine u plus c, right? Okay. And is it bothering you guys that I'm not, like that 1/5 isn't being distributed to the c? Is that weird? It's not a problem because do we know what the c is? What is the c? Just some constant that we don't even know what it is anyway, right? So what's some constant times a constant? A constant, right? So we don't have to mess with writing that as, we don't have to do this. This would be overkill for us to say something like that. We don't need to. Distributing a constant to a constant still just leaves us with a constant. Does that make sense? So we can get a little lazy with that guy. Okay? And then if we reverse the substitution here, what do we get? Cosine 5x plus c, right? This cake. That was no big deal with that u substitution. Right? Okay, now let's try, how about this one? Once again, the hardest part here is just making the right u substitution, but don't be too fearful about picking one, because the worst thing that can happen is you pick the wrong one and you try another one. And there are some cases, I'm going to give you, not many, but I'm going to, just so you can see what happens. You may get a problem or two that u substitutions just don't work on. And you got to, see that. That's, sometimes they don't. In fact, in real life, most of the time they don't. You got to do something else. Yeah, 2x plus 1 makes sense here, doesn't it? Yeah. Because if we just had, like the good old days, not that long ago, if we just had the integral of the square root of x, that's a piece of cake. That's just x to the 1/2. I use the power rule. What makes this complicated is that inside the square root, I've got more than just a plain x. So the part that's complicating this is that part. So that would be our logical choice for the u substitution. Okay, so then what, if we differentiate, what is du equal to? 2 dx, good, okay. And, everybody agree? Okay, if we make our substitution then, what do I end up with? Square root of u, which I might as well go ahead and just write as power. U to the 1/2, and then the dx, 1/2 du, if I solve for dx, right? Okay, so my answer then is, I'll leave the 1/2 out there, and we just did this one, right? The antiderivative, or the integral of u to the 1/2, 2/3 u to the 3/2 plus c. So 1/3, and in this case I've got the quantity 2x plus 1 to the 3/2 plus c, right? Okay. Now, let's take one very similar to that. Very, very similar. I'm going to make one little tweak to this, and it messes things up. So, almost the same problem. Okay, once again, the problem is what's inside the radical, right? Okay. So what if we do that? So that's our u, right? And just like before, du just equals 2 dx. Okay, let's make our substitution just like before. Just like before, I get a u to the 1/2 times a 1/2 du, but I've only accounted for those parts. Whoops, I've still got an x in there. So it didn't work. So it is all lost. Well, maybe not. Maybe not. Does anybody have a suggestion here? How could we, that's an incomplete substitution. Does anybody see how we could complete this substitution?
You do double substitution.
I mean, there are cases where we may do something like that, but we don't need to here. Ah, why not? Look, we've got a substitution equation right there, right? That relates u to x. That's the job of that equation, is to show us how the u is transformed to an x. There's the equation that relates the two variables. Now, in this case, because that's a simple equation, because it's linear, right? The u's and the x's are linear. Now, if that had been something like, 2x plus 1 quantity squared, or something or a trig function, that would have been more complicated, and solving for x in terms of u would have been problematic, because maybe it would have had multiple solutions, and then we'd probably say, okay, this isn't working, and later on we'll have a better way of doing it. But this was an easy substitution. It's very simple for us to solve for x in terms of u, right? So if we do that, if I solve for x in terms of u, what do I get? What do I get? After those two steps, what do I get if I solve for x in terms of u? U minus 1 over 2, okay. Okay, so I could make that substitution. Right there, right? I could pull the 1/2 out front. Okay, and I end up with then, if I complete the substitution, I got a 1/4 out front times this x becomes the quantity u minus 1 times u to the 1/2 du. And can I go from there? What do you think? You want to suggest what I do next? Well, I got to be able to take the integral. That doesn't quite look like a standard form yet, but this looks more like stuff you've already done. I could distribute, couldn't I? What if I distribute the u to the 1/2 over that binomial? That's not a big deal. I'm just going to get powers of u, aren't I? My fractional powers, but that's all right. So I get 1/4 times the integral of, what's u times u to the 1/2? U to the 1 times u to the 1/2, what do I do to the exponents? Add them. So that's just u to the 3/2, right? 1/2 minus u to the 1/2 du. Now I'm able to integrate term by term. So what did we accomplish there? You know, if you think about that, we ended up with u's and x's, and then when we completed the substitution, we still got something fairly ugly, but it wasn't nearly as ugly, because even though we had to distribute and we get multiple terms, we still accomplished our original goal. Our original goal was to get a simple argument inside the square root. Even if we traded that for some complicated stuff outside the square root was the hang-up, wasn't it? And so that u substitution still accomplished our goal. We still were now able to do the problem relatively easily. So what does this give us for an answer then? We get 1/4 times a bunch of stuff. What's that term going to be? The antiderivative, or the integral of u to the 3/2 is 2/5 u to the 5/2, right? And then minus 2/3 u to the 3/2 plus c. And now what's left? Yeah, reverse the substitution, and we're done. So 2/5, instead of a u, that's going to be, what was our 2x plus 1. Sure, that's a little complicated, but big deal, it's the answer. We're done. And it's a function that we could use. Okay. Questions? Does that make sense? Okay. So really, the last major issue then is, how do we translate this into definite integration? Where we're finding an area under a curve, and this is really cool. Do with this. It makes this just as easy, if not easier. Okay, let's look at an example, and there's really nothing additional to show you here, but I just want to show you how easy it makes it. Okay, let's try this guy. Let's pick one out of the book. So what if we want to do the definite integral of x times the quantity x squared plus 1 cubed dx from 0 to 1. Okay. Now this is one that we could do the old-fashioned way, isn't it? We just expanded the binomial and distributed it. But why not make a u substitution and make it much easier? What's the u that fits here? X squared plus 1. So if we make that substitution, u equals x squared plus 1, what's our du? 2x dx. Okay, and so we can make our substitution, right? We just get, instead, this part right here just becomes a u cubed. Agreed?
Yeah.
Okay. Now what's this? X. Now, and we really need the x and the dx combined are that, right? And what are they equal to? Okay, du divided by 2, a 1/2 du. So there's our 1/2 du. But now notice what we've got going with our limits of integration. These are still written in terms of x's, right? So what are our options here? Well, we could finish the problem just like we've done. We could get the answer, reverse the substitution, write it in terms of x's, and evaluate from x equals 0 to x equals 1, right? Just the way we normally did all the problems we've done today. We got answers in terms of x's, right? We could do that, but don't. There's a much easier way to do this, much easier way. Let's just say no to these x's, and let's write the limits of integration in terms of u. And the way we do that is we just go to our substitution equation, right? And we ask ourselves, okay, when x equals 0, u equals 1. So we make that just a red 1 instead of a black 0 at the bottom, right? When x equals 1, u equals 2. So we make that a red 2. How cool is that? We don't even have to go back to x's. This one actually ends up being an easier problem. So our answer then just looks like we got a 1/2. The integral of u cubed is all once. U to the 4th over 4. Okay. And we're just going to evaluate this from 1 to 2, right? So we can pull the 1/8 out front. And u to the 4th from 1 to 2, that just means 2 to the 4th minus 1 to the 4th, right? Everybody agree?
Yeah.
Which is what? 16 minus 1, so 15? How about that? That is pretty amazing to me. That works. Now I want you to see what we did here. This is so super cool that you probably haven't really thought this all the way through yet because it's so new. But let's look at the graphs of those functions. I've got some fancy program to do this, but I don't know if I can get it to work right. Let's see. Okay, let's try this. I'm probably better just using the calculator. Yeah, I'm just going to use calculator. I don't know how to use this one very well.
You use that one, didn't you?
Yeah, I did, but I haven't used it enough to do calculus. So I need to play with it a little bit. Okay, so let's see. Oh, I know what I should do. I think I can do. Oh yeah, okay. I just want to have the graph. Never mind. I'm just going to waste time. Okay, so, well, that's what I want, large screen, right there. Ha. There we go, okay. Perfect. All right, so let's go back and graph these guys. I got to show you that. If you don't know how to use that polysmult too, I got to show you that one to you. That's a good one.
We learned that one time.
Did I show that to you?
I think, like last year we got.
Oh, did I? Okay. So let's look at the original one here. Let's put this guy in, right? So if we want to find the definite integral, so we'll go y equals, and we'll just put that, we'll put in this function and ask the calculator to find the area graphically. So we've got x times the quantity x squared plus 1 cubed.
Oh. Oh, that's not good. Huh. What's that? Up there it did? Oh, I wonder if the bulb burned out. A red light's usually not a good thing.